Thank you very much for taking the time to attend this latest installment in the Interacoustics Academy webinar series. The title of this session is to provide an introduction to the rotatory chair. First of all, we'll talk about the sinusoidal harmonic acceleration, then the VOR suppression test, and then the velocity step test. Now, the first and the last of these three, these are aimed at assessing the peripheral vestibular function, whereas the middle one, VOR suppression, this is a test of neurological top-down influences on the VOR. So it's a test which isn't sensitive to peripheral vestibular disorders per se, but neurological disorders, central neurological disorders that may affect the vestibulo-ocular reflex. And the neural mechanisms involved are similar to those that we use during the smooth pursuit task. So if there's an abnormality of VOR suppression, it might well be that there's an abnormality in the smooth pursuit test that we also usually include in the vestibular test battery. So they used similar neural circuitry, which will include elements of the cerebellum, the brainstem, the visual cortex, of course, and frontal regions of the cortex as well. So wide-ranging, not very localizing, but nevertheless a useful subtest to have in our disposal. Now, but before we get onto that, let's go through the sinusoidal harmonic acceleration. So what we have here is a top-down view on the left of an individual. This is the head of that individual sitting in a rotary chair. And if we are to spin that person smoothly to the right, and it's a continuous rotation, then here we have on the right hand side of the screen that schematic that I just showed previously. So the right here was the leading ear, and that senses that rightwards head rotation with an excitatory response, and the trailing ear, the left ear, an inhibitory response. And so we have this eye movement, this compensatory eye movement, and that compensatory eye movement will be directly proportional to the head rotation. So that's how we get some indication of the sensitivity of the ears there. And what we actually would see, at least with a continuous rotation, is this concept known as nystagmus, which I'll just briefly run through right here. So we have on the x-axis time, and on the y-axis distance, and this is distance of the eyes moving in their sockets. And this is a red trace showing the right eye, although we might plot a similar trace for the left eye. And so this is as the eyes move to the left, then the trace moves down on the screen, and then as the eyes rotate to the right, then the trace moves up on the screen. So we can see that with a right headwards rotation, as we just showed previously, the eyes will drift to the left, and with a continuous head rotation, at some point that drift will be interjected by a fast phase, a saccade. But what we're interested in is the slow phase. That there shows us directly the movement of the copula in the right and the left ear. So that's what we're interested in, and we, to a large extent, in the rotary chair test battery, we ignore or filter out, if you like, these fast phases. And so the direction of the nystagmus, so that was where the slow phases were to the left, and then the eyes were beating, the fast phases to the right. But the direction of the nystagmus reflects the direction of the rotation, because if we had leftwards smooth head rotation, then we would get a rightwards eye movement, slow phase, and then a fast phase beating to the left. So directly the opposite of what we just showed. Now, a very important feature for understanding the slow sinusoidal harmonic acceleration test is that for these low or slow accelerations, both ears contribute to moving the eyes in either direction. So the rotary chair test, it's not an ear-specific test. And this slide attempts to explain that concept in brief. So here we have the stereocilia for the left ear and the right ear, and we know that it's a leftwards head rotation because the stereocilia are in blue, and the stereocilia are moved on the left ear towards the larger, the kinocilium. That gives an increase in nerve activity, while at the same time the right ear, the stereocilia are moved away from the kinocilium. That gives a decreased nerve activity. So we have this reciprocating or push-pull relationship between the left and the right ears. Now, if we were to rotate the head the other way, then we would have the opposite pattern of activity. So again, the stereocilia in red now showing we've got a rightwards head rotation, and the stereocilia on the left ear are bent away from the kinocilium, so we have a drop in neural activity, whereas these stereocilia are bent towards the kinocilium, and so we have an increase in neural activity. And this sinusoidal pattern of neural activity and therefore eye movement, this constitutes the basis of the sinusoidal harmonic acceleration test. For a higher, just as an aside, for a higher acceleration, and this is a very important concept when it comes to the video head impulse test, but for a higher acceleration, both ears may not contribute to the response at all times. So here we have, just for instance, when the stereocilia are bent in the excitatory direction, we can have a large increase in firing, but in the scenario where they're bent in the inhibitory direction, there will be a baseline below which we can't go. And so that ear is the ear in which this hair cell might reside is prevented, if you like, from contributing any further to the response. But to a large extent, the rotary chair test doesn't get to the high levels here, which might lead to this effect, because the head will become more and more unstable on the headrest, and you'll get head slippage. So we tend to limit ourselves to slower sinusoidal accelerations. But I mentioned that the direction of the nystagmus will reflect the direction of the head rotation. So here we have the right beating nystagmus showing a right head rotation, and then here we have the left beating nystagmus showing the left head rotation. Now, when it comes to the results of the sinusoidal harmonic acceleration test, then this is what we end up with. We end up with, as the green line here is the stimulus, that's the head stroke chair rotation, and the eye movements will then alternate between left beating showing a left head rotation, and then right beating showing a right head rotation. And when we rotate the chair repeatedly from side to side, then we can build up a trace where the pattern of the ensuing nystagmus constantly flips from right beating to left beating to right beating to left beating, and so on and so on. Now, if we take the slow phases at each point in this cycle and plot those slow phases, now the slow phases are meant to be equal and opposite velocity to the head rotation, and so that's what we see on this lower chart. So the green, just to remind you, is the head rotation, and then these plots, red for right eye and blue for left eye, are the slow phases at each point on the cycle. And since the slow phases are compensating, the slow phase of the eye movement is compensating for the head movement, then we end up with a sinusoidal wave that's 180 degrees out of phase. It's the same amplitude but going in the opposite direction. This is but this was a brief video showing the procedure for the sinusoidal harmonic acceleration. So what would have happened had we had a chance to watch the video would be that the patient in the chair swings smoothly from side to side as we then build up the trace as we just saw it on the screen a few moments ago. And so the patient is rotated in these alternating directions And we can do this at various different speeds, or you might say octave frequencies. And one of the major advantages, if you like, over the chloric is that the chloric is limited to just a few sort of strengths of stimulation, which relate to the temperature gradient that we can set up. We might do standard temperatures and maybe sometimes ice cold chlorics. Whereas in the rotary chair, we can build up a wide range of a picture of the response of the VOR across a wide range of head rotations, approaching those which you might perform under normal circumstances, real life. And the first few cycles are often discarded just because of data quality issues, while the patient kind of gets used to the stimulus and the mental alerting reaches a stable state. And then a few cycles at each frequency will allow us to then average the slow phases and produce a relatively robust result, which I'll just go through in a moment. One disadvantage, though, is that it's a relatively, or it can be, if you were to do all these frequencies, it can be a relatively lengthy procedure. And that's because certainly at the lower frequencies of oscillation, so one cycle at 0.01 hertz would be 100 seconds, and we might do 2 cycles at each octave frequency. So you can see quickly the test time will build up there. And so to get around this, it's often the case that you might do a screening protocol. For example, you might do 3 frequencies, a medium, a high, and then a low frequency, and under many circumstances that might be sufficient, and it might just be necessary to carry on with the other frequencies when results are perhaps abnormal or inconclusive on their own. And so we average the results over several cycles, maintaining as best we can mental alerting, so getting the patient to do a mental recall task or some of the simple mental arithmetic or so on, just to maintain arousal at a fixed level throughout. And so there are 3 elements in which we can interpret the results of a sinusoidal harmonic acceleration test. These are gain, phase, and symmetry values. So I'll just cycle through each of those 3 in turn. So the first one is gain. So we have here just a snapshot of one cycle at one frequency, and we can see the green line is the head rotation, and then the red and the blue dots are the of the eye movements, the slow phases, which are equal and opposite. And so what we do is we measure the maximum eye velocity, which I've just displayed with the arrows there, and then we measure the maximum head velocity. And if the VOR is working kind of optimally as we think it should, then we would expect a gain of 1. And if there is a reduced sensitivity in the VOR, the peripheral vestibular system, and the neural connections from it, then we might expect the gain to drop below 1. So what we can see here is just a schematic of the results as you might see them, and this bullet point here just reiterates what I've just said. So if the VOR provides perfect compensatory eye movements, then gain should be 1. And you can see that certainly for the higher frequencies, so 0.32, 0.64, 1.18 hertz, then it's possible to get up towards that magic 1 around here. Although it's also the case that the normal range, even in these higher head rotations, falls somewhat below the magic number of 1. But when we move down into the range where we commonly do test with the rotary chair, then even under normal circumstances, the gain might be below 1, below perfect. And the reasons for that might become clear in a few slides' time. But for now, just bear in mind that we have this normal range, and what we expect to see if we were to follow that screening protocol would be the gains falling somewhere within the normal range for the medium, the high, and the low frequency oscillations, and similarly if you were to do the intermediate octave frequencies as well, then that's where we'd expect our gain values to be. So eye speed divided by head speed. And then if there is an abnormality, and please note, because the chair is is not an ear-specific test, then it could be either a unilateral or a bilateral weakness that we're talking about here. Then we would expect systematically for the gain to become reduced or lower than the normal range. And what we have here on the left is a typical pattern, as you might expect, with a unilateral weakness on one side or the other. And with that unilateral weakness, then now the average gain, which is, remember, that's averaged across several cycles, in other words, a rotation in one direction and the other. And so for part of those rotations, the ear that's leading, if that's a weakened ear or reduced function, then the leading ear, leading in terms of the direction of the head rotation, it won't produce or won't contribute correctly to the VOR, and then so gain will be mildly reduced. And it's often more common to see that mild reduction in the lower frequency rotations, whereas if you increase the speed of the rotation, the acceleration is greater, the copular deflection is greater, and so any residual function might therefore draw the results back somewhere in the normal range. Now, if you had a bilateral weakness, you'd expect a similar pattern, but because the effect is now the case in both directions of rotation, then the effect size is greater. So rather than a mild reduction, you might see a slightly greater reduction, but when you increase the speed of the rotation, it might be enough to draw the results back into the normal range. Whereas if you had a severe reduction, a severe weakness, then of course you might expect that despite the strength of the stimulus increasing, there was limited or no perhaps sensitivity to that rotation, and so the gains are systematically low. So we can also have a look at the symmetry between these two these gains. So how was the gain when we rotated the head to the left compared with to the right? And please note, this doesn't lateralize the side of a deficit if it was a unilateral deficit, but what it does do is it would reflect a certain bias in the system. So for example, if you had a left beating spontaneous nystagmus and then you rotated the head to the left, you might expect the spontaneous nystagmus to add on to the stimulation and then cause a bias, whereas if you rotated the head to the right, that rotation would normally cause a right beating nystagmus, so that would interfere destructively with the left beating spontaneous in that example and create a bias. So in some ways this measure is a similar concept to the directional preponderance that's sometimes discussed in caloric testing. So it can reflect a certain bias in the system, but it doesn't give you lateralizing information to do with the ear of the suspect ear if you did suspect a unilateral weakness. And then finally, the other information that comes from the sinusoidal harmonic acceleration is phase. And then this is a timing relationship between the eye movements and the head movements. And if we had perfect timing, then the eyes would be moving 180 degrees out of phase, in other words, equal and opposite to the head movement. And what happens in reality is that in fact we get something of a phase lead, and I've shown that where these little red arrows showing that the peak of the eye movement occurs a few moments before the peak of the head movement. And this is particularly pronounced with low frequency head rotations, and then it gets less and less pronounced as the speed of the head rotation increases. And that's under normal circumstances. So it's perfectly normal to see this this effect here. And I'll take a few moments to explain or attempt to explain the cause of that effect, which is essentially an overcorrection. So the head rotation and the eyes, at least in low head rotations, overcorrect for the speed of the head rotation, and they lead it. But then what happens in the case of a vestibular weakness is that this overcorrection for low speed head rotations, the effect of this overcorrection is increased. So you get a gradually increasing phase lead. So if the phase lead is abnormally high, this can actually indicate a vestibular weakness, either unilateral or bilateral. So here's how the phase lead might appear on the results here. So we have the different frequencies of head rotation, and then 0 phase lead, and then below would be a phase lag, and then above the horizontal line here will be a phase lead. And so as you can see, as the speed of the head rotation decreases, we get progressively a greater and greater phase lead, an overcorrection in the slow phase velocity of the eyes. As the speed of the head rotation increases, that phase lead comes back to somewhat towards 0, which is where we would ideally want it under optimal circumstances. And here's what can happen, for example, in the case of a bilateral weakness. So on the left here we have the gain, showing the pattern that we described a few moments ago, gain reduced in the low, and then with a slightly stronger stimulus it can be enough for to make use of any residual function with symmetrical gains to the right and to the left. But what we have here, as you can see, is in this case of a partial bilateral weakness, we have a progressive phase lead as we go down in head rotation. And if this was a complete bilateral weakness, the size of that phase lead would be even greater, so the slope of this line would be steeper. And I'll just take a few moments to attempt to explain exactly where this phase lead comes from, and then also why it is that the phase lead gets even bigger when we have a vestibular weakness of some sort. So what I'm displaying on this slide here, I'll just draw your attention to the top schematic. So we have time, and then we have the strength of the stimulus. And as an individual is moving from stationary and then increasing their speed to then become a stable velocity, then what would happen here, you can imagine the patient spinning in the chair, and they would be spinning up to speed and then reaching a constant speed where they'd continue to spin. And at this point, then I'll just draw your attention to the yellow traces which show the acceleration. So at the as the speed, as the velocity is increasing, then we have a constant acceleration. Then when we reach the target velocity, there's no more acceleration, and then the acceleration curve drops. Now the second schematic just below, this shows the copular deflection in the inner ear as a function of this acceleration and velocity. And you can see that the deflection of the copula comes from 0 to a maximum point that goes in time with the acceleration, not with the velocity. So as the head is accelerating here, we get partial deflection. When we reach the maximum copular deflection is when we reach the point of maximum acceleration, and then when the acceleration drops to 0, there's no more pressure differential across the copula, and then the copula becomes centralized again. What this means is that despite the fact that in this example the patient is continually spinning around, there's no copular deflection. So if they're in darkness, then they would perceive a drop in the speed of the rotation, even though you can see that from this schematic that the rotation is steady. So this is meant to highlight that the copula responds specifically to acceleration, but the eyes, of course, they move. We talk about slow phase velocity, not slow phase acceleration. So the eyes, to compensate for the head's rotation, the head's velocity, they need to have a slow phase velocity accordingly. So the input is acceleration and the output is velocity. And when they reach this steady state, this velocity here, and the copula is deflected and they perceive a drop in rotation, then there are a few cues left open to tell the patient that they're still spinning. For example, the localization of any sound in the room, and maybe the light breeze against their cheek as they're spinning around. But they won't be getting any information from their ears to tell them that they're rotating at this point. And now what I'm displaying on this slide, again, just to clarify, so just an attempt to explain the phase lead, is the quite commonly seen Bode plot showing the pendulum model of the VOR. So I'll draw your attention to the bottom half of the trace right here. What this shows here is we have on the x-axis we have the speed of the head rotation, and on the y-axis we have the phase. And I've divided this chart into three sections. We've got on the left a slow head rotation where we have a phase lead. In the middle we have the normal range of head rotation, so the phase is around 0. And then on the right hand side of the chart, this shows a fast head rotation, and that's where the head is moving so fast that the signal from the ears to the eyes, which has a latency of to it around about 7 to 10 milliseconds, so it's not quick enough to get the signal from the ears to the eyes, and so the eyes, the slow phase velocity of the eyes will lag behind the head movement, and so we have a phase lag. So the question was about the source of the phase lead that we see with the slow head rotations on the left of the chart. And it's the issue is that we have the input signal, as I mentioned, is an acceleration signal, and that's a signal that's converted centrally by the sort of so-called neural integrator, or the velocity storage mechanism. And acceleration is a first derivative of velocity, and it leads by a quarter of a cycle. So at slow head rotations, the eyes overcorrect, and as the speed of the head rotation increases, then the overcorrection is cancelled out, and that's what we end up with in the middle part of the chart. And so why does this overcorrection due to acceleration being converted to velocity, why does this get worse when we have a vestibular deficit? Well, the second stage of the VOR, that's the velocity storage stage. The first stage is the displacement of the copula in the first place. But the second stage of the VOR, that's like a positive feedback loop. Positive meaning that the neural integrator requires input from both labyrinths to convert the acceleration signal into a velocity signal. And in vestibular deficits, this integration is missing, or at least partial. And so, without the initial input, then the conversion can never occur, and the effect is exacerbated.